Hello, welcome to the lab on force, mass, and acceleration. I'm Dr. Brian Toms. I'm here with Dr. Sumit Delaware, and we're going to walk through the lab and help you take some data. Now notice we have the apparatus set up here, and what you'll see is there's a cart. I'll zoom in a little bit here. Right now we have a block in front of it to keep it from moving. We have a cart stop at the end, just where our end line is, and there's a little hook, and there's a string attached to that hook. You can't see the string all that well. We'll zoom in a little bit. There you go. And that string is attached at the other end. It goes through a stop and it is attached to a pulley. And that pulley is attached to a hanger that weighs 5 grams, not very much, and we can add additional mass to that. So that will provide the tension in the string that will pull the cart along. All right. So I'll zoom back out a little bit, walk away here, and you'll see once it focuses, that the mass on the right is hanging down over the pulley. It will provide tension in the string that will pull the cart, in this case to the left, but the cart is arranged so that when we record the data, that's the positive direction. The direction the cart is moving is the positive position, velocity, and acceleration. We have leveled the track so that when there's no tension on the string, that the cart won't slide. So what we want you to do first is question 1 is to look at this situation, identify the forces on the cart, all of them, right? When it is sitting, but also when it moves. So let's do a demonstration of what it's going to look like when it's actually moving. Dr. Delaware will remove the black block and let it go. And it will accelerate. There we go. Right? And so as it's moving, that's when the data is going to be taken. You're going to identify what the forces are, and you're going to draw a free body diagram. So please stop the video and go ahead and do question 1. Now that you've completed question 1, we want you to look at that situation, look at the forces that are on the object, and go on to question 2. Question 2 is very important because it's your predictions. And you're going to predict what the velocity versus time, acceleration versus time, and force versus time graphs are going to look like. Predictions are very important because they bring out what you're thinking. And your ideas can't change unless you acknowledge what they are. So we need to know what you're thinking. Predictions are never wrong in these labs. Predictions are a way for you to express your idea and then test those. And that's what science is all about. It's about testing a hypothesis. So please stop the video, make your predictions before starting again, and then we'll take some data and we'll test and see whether your predictions are good or whether we need to change the way we're thinking. Now we're ready to start part B, where we're going to take some data. And the first thing we're going to do, and we're going to do this for each of the runs, is we have to zero the force sensor to make sure that when there's zero force, the sensor reads 0. So you'll see what Dr. Delaware is doing. He's putting slack in the line, so the string is providing no tension. And then he's going into a capstone program where we're taking the data, and he is finding the menu to zero the force sensor. Okay. So we do that with each run to make sure that our data is good data. Right? And what he's going to do is he's going to start the data collection, which is going to collect velocity, and I'll show you the graphs here. On ours, we have a velocity graph, that's the large one on the left, and then acceleration and force are the 2 on the right. And we're going to be providing the data that we take together to you in an Excel file. So we're going to record this data. And notice that he's going to start collecting data before he releases the cart. And so the first data that's taken is not data that is the data we're going to analyze. You want to analyze the data only for the time in which the cart is being pulled freely by the string, not any effect of Dr. Delaware, and before the mass hits the ground, right? And you'll notice that the graphs will change once either the cart hits the stop or the mass hanger hits the ground. Okay, now Dr. Delaware is going to start data collection, and then he's going to release the cart. There we go. And let's take a little look at what the data looks like that you're going to get. First, there's the velocity versus time. And you can see the shape of that. You can see at the end something changes very abruptly, and now we know that that's not part of the motion we're looking at. We have the acceleration versus time. And again, you've got to look only for the time period, and you can use this velocity versus time data to figure out what the time period is for the data that is valid in this experiment, right? And then we could take the data for that time period to find the average acceleration. And then when we look at the force versus time, we can also use that same time period to take to find out the average force. So there's the data you have to analyze. Okay, so we're going to provide you that data. You're not going to analyze the data that you just saw on the screen. You're going to get an Excel file because you're going to need to plot the data yourself in order to analyze it. And when you plot the data, first of all, you're going to plot and look at the graphs, and you're going to compare them with your predictions. And then in the next step, what you're going to do is you're going to analyze the data to find the average acceleration only during the part of the motion at which it was being pulled freely by the string. In other words, matches your free body diagram. And you can do that either with the acceleration versus time graph or by fitting a line to the velocity versus time graph. So you have two options. And you're also going to find the average force, and you're going to use the force versus time data. Again, you have to make sure that you restrict yourself to only the time period that's the right time period, and not use the data before he let go or after the weight, the mass hanger, hits the ground. So now you get to analyze that first set of data and answer those questions. That would be questions through question 9, and then we'll start again with part C. So come back and start the video after you've finished all the questions for part B. Now we're on to part C, where we're going to change the tension in the string, and we're going to analyze the data to look at the average acceleration and the average force when we're applying different amounts of force. To do that, we're going to change the tension in the string, and here's how we do that. You can notice that we put a little extra mass, another 10 grams on top of the 5-gram mass hanger. So that's going to create a higher tension in the string. Dr. Delaware has already zeroed the force sensor. Now, the data run that we've done previously in part B with 0 extra mass is already the first line of your data table 1. So this data now is for the second line of data table 1, sorry. So Dr. Delaware is going to go ahead and take that data. Starts the collection, let's go, and there we go, all right? And here we have our velocity, our acceleration, and our force graphs that you're going to get, right? And now we're going to go on and we're going to add an additional mass. Now we've got the hanger plus an additional 20 grams. Okay. Just lining it back up so it's back on the pulley. He's going to zero the force sensor. I need some Jeopardy music to play while we do that. Okay, and now he's ready. Now the force sensor is zeroed again, and he's ready to take the next data run. This is hanger plus 20 additional grams. There we go. We got the data there. And we're going to do one last run, which is the hanger plus 30 grams. We won't show you that. It's going to be in the data file. The Excel file will be provided to you, which will have that first run, but then also 3 additional runs with 10 grams, 20 grams, and 30 grams of extra mass. For question 14, it asks you to determine the mass of the cart, so let's do that. Here's our scale. You can see it's reading 0 grams. Here's a cart. I'm going to turn it upside down in order to keep it from rolling. And there you see the mass of the cart. So that's question 14. That should be all the data you need in order to complete part C. Now we're going on to part D, where we're going to examine changes to mass in the cart. We're going to use a constant or nearly constant force for this. We're going to measure the force each time. So we're going to see if it changes a little, but it'll be nearly the same. And we're going to do that by hanging 20 grams on our 5-gram mass hanger, and that will stay the same for this entire part of the experiment. What we are going to change is the mass of the cart. And the way we do that is by adding 250-gram masses, these black rectangles, to the cart. Now the first data point in your table is data you've already taken. It's for 20 grams on the hanger and no additional mass. The next data is the data we're taking here, which has 20 grams on the hanger, which they all will, but has an additional 250 grams on top of the cart. We've already zeroed the mass hanger, and so now Dr. Delaware will go ahead and take this data. Okay, and if we look, we see that we get a shape very similar to what we've seen before, and you'll get this data in a data file, right? And you'll be analyzing it, and we're going to be adding additional mass, right? We won't show you all of that data taking because it will look exactly like what we did right here, but we will be adding additional masses, right? So 250, we'll add 2 masses, that'll be 500, 3, and 4, right? And that's the data that will be included in the Excel table. Enjoy.